Hello, everyone. My name is Sahil, and today I'll be talking about supermodular approximation of norms and applications. This is joint work with Thomas Kesselheim from University of Bonn in Germany and Marco Molinaro, who's from Rio in Brazil and also with Microsoft. So this work is about optimization problems where the objective is norm. So you might have some norm objective and you want to minimize, maximize, and so on. So let's recall what the norm is. Norm in n-dimensional space. So we'll be in this work, we'll be focusing on finite n-dimensional problems, and we'll be only working in the positive orbit. So we'll be working with non-negative vectors, because many of these applications are applications, they only work with non-negative vectors. So a norm is nothing but it satisfies the three properties: homogeneity, we use by a scalar, and the norm increases by the same factor, triangle inequality, and the vector norm is zero if and only if the vector is all zero vectors. And as I was saying, we are interested in optimization problems where you want to optimize a norm objective. And some classical norms are the L infinity norm. You want to kind of like minimize the max or something like, which is the max of the maximum coordinate. L1 is the sum of the entries of the coordinate, and LP norms. And they have like many different motivations for different applications. But besides continuous optimization problems, you can actually often write many discrete optimization problems in terms of norm objectives as well. Like some problems include like load balancing, where you have jobs being assigned to machines, and you want to minimize maybe load on the maximum machine. So L infinity norm or LP norm objectives talk about facility locations, about connection cost, set cover, sanitary. Some of these problems I'll talk later as well. But yeah, many of these optimization problems, they can be studied for norm objectives. And the main motivating question for us is that how can we go about designing good approximation algorithms, good algorithms for norms, when the norm is more general than LP norms. So if I go beyond LP norms, like this general definition of norms that I just defined, how can we go about designing good approximation, good algorithms? And when I say good, I mean polylogarithmic approximation. So all norms are equivalent up to some poly n factor, that is the number of dimensions. But if you're interested in polylogarithmic, then things become not trivial. So we are really interested in getting approximations or guarantees, which is, we are fine losing some polylogarithmic factors, but not poly. And this is interesting both because, first of all, this is mathematically interesting. General norms are basically any convex body represents a norm, so it improves our understanding of general convex bodies. And also it can allow us to capture many more interesting objectives and applications, like energy and many more, which require us to deal with like beyond LP norms. Right? And so to motivate a bit more, like norms appear also in many other contexts, and they often appear in a hidden sense. Like for instance, any norm, first of all, you should be thinking of a norm often as nothing but a maps of linear functions. So this is because any norm, it has its dual representation as well, where you look at all vectors W in the dual unit ball and just look at X dot W. So this is an equivalent definition. Any norm can be written in this form. And because we're working only with monotone norms, like norms which only increase as I increase the coordinate, then you may as well assume that these vectors, like these non-native linears, are also positive. And like there are lots of applications where you often talk about like often minimizing the norm objective. Here's a very different looking objective: set value functions. So think of something like submodular functions or subadditive functions. So these are functions which are defined on the hypercube, basically for any subset of elements. What's the real function value? And consider set value functions which can be written as maps of additive functions or maps of linear functions. So this class is precisely known as XOS valuations, XOS set functions or fractionally subadditive functions. These are nothing but, as I was saying, like a function where the value for any set is nothing but look at the indicator of that set, dotted with the weight vector and maps over all W's. So what's interesting is these functions are known, XOS functions or fractionally subadditive functions are known to capture submodular functions. So any submodular function can be written in this form. And any subadditive function can be within a log factor can also be written in this form. Hence, in some sense, studying norms also can give us intuition and better understanding of general subadditive functions or general XOS functions, submodular functions. Usually these set value functions, when you think about them, we don't think of them as norms. But what I'm saying is that they have close connections because both are nothing but maps of linear functions, maps of non-negative linear functions. And these set value functions like submodular optimization is a big field, minimization, maximization, you study many variants. another different objective is the packing constraint. So I give you an arbitrary packing constraint, and you can define a rank function for this. Like packing constraint means like say cardinality constraint, matroid constraint, intersection of matroids. You can define independent check constraint, like any arbitrary packing constraint. If you look at the rank function or even the weighted rank function of this, that's nothing but a max of linear functions. So what I'm saying is like norms are nothing but max of linear functions, and max of linear functions appear in many, many different forms in different fields, as constraints, as minimization objectives, as maximization objectives, and so on. So all these three objects are very intimately related. And that's another reason why studying general norms is very interesting. Okay, so going back to our original question. So the main motivation question is, how do we go about designing good algorithms beyond LP norms? Okay, let me give you one more example of an interesting norm family. These are known as symmetric norms. So these are something like a subclass of norms which have been greatly studied, at least in the last 5-10 years. Like here are a few citations as well, but I mean, there are many more that I'm missing. So these are norms which are invariant to renaming coordinates. So if I start calling coordinate 1, coordinate 5, then it should not matter, the norm. And classical example is the LP norms. LP norms, if you rename, it doesn't matter. There are generalizations of LP norms to all H norms. There are top K norms. There's another interesting class of norms. Top K is where the norm is the sum of the largest K coordinates. So these are known as top K norms. So top one is nothing but the L infinity norm, and there are generalizations of this. And you can also take like perform many operations on symmetric norms, like positive linear combinations, compositions, and norms of sorted vectors. Like many of these operations, they also preserve symmetry, and hence, so this class of symmetric norms, this is very powerful and it captures many applications. Hence, it has received a lot of interest. So again, the question we are asking is, okay, how do we go about designing good algorithms for these symmetric norms, which is beyond LP norms? So the first question maybe we ask is like, okay, what's special about LP norms that makes them so much more friendlier? So usually like good algorithms for LP norms work by writing the norm as sum of xi to the power p. Okay, so this is nice because of two reasons. First is it makes the function separable, the norm function separable, like linear, like it's written as a decomposition of different coordinates, their contributions. But this is like a very strong property of LP norms, which is not really achievable for general norms. Another interesting property of norms, which might sound somewhat innocent, is like if you look at the gradient of this norm to the power p, this function has very simple structure, like p times xi to the power p minus 1. In particular, this is non-decreasing. So if I increase any coordinate, the gradient, the ith coordinate of the gradient will not decrease. So it's a non-decreasing function. And this is the second property which will motivate us to define this class of supermodular norms. So we say a norm is supermodular or is p supermodular if the gradient of that norm to the power p. So like for LP norms, if you look at the norm to the power p, look at its gradient, as long as this gradient is non-decreasing for all the coordinates. This is we call p supermodular norms. So LP norms is one example, but we'll soon talk about like other norms which have this property. Okay, and equivalently, this can also be written as like, because you have gradients are increasing, you can also write it in terms of like the increase in marginal gain, like u plus v plus w to the power p minus u plus v to the power p is at least u plus w to the p minus u to the p, which is basically saying increase due to adding w. This only increases as you go from u to u plus v. Okay, these are equivalent definitions for differentiable norms. And a couple of remarks like norms, although norms are monotone, their gradients need not be given for L2 norms. If you look at its gradient, that's good decrease. And already very simple looking norms like L infinity norm or L1 plus L2, they are very far from being p supermodular. One can construct that you need p to be super large, like polynomial or even larger, to make it p supermodular. So in general, norms are not p supermodular. Okay, so then one might wonder like, why is this property so interesting? The reason is that although the norms may not be supermodular, you can often approximate them pointwise within like some constant factor or some small approximation factor with a norm which is supermodular, which is p supermodular for a small value. Like we'll be interested in p being roughly logarithmic. So the simplest example is L infinity approximated by L log n, and that's like within a factor, constant factor. And this is now a log n supermodular. So our first main theorem says that any symmetric norm can be approximated by a p supermodular, when where both the factors are like log. So you can approximate any symmetric norm within a log factor by a log supermodular. So this basically says any supersymmetric norm, which is like a very large class of norms and which have been studied a lot over the last decade, this norm can be made supermodular. And then for special subclasses of symmetric norms and like other norms, we can also obtain better approximation factors. In the paper, we also discuss some other norms, but one of the most interesting class is this symmetric norm. But for top k or rich norms and other norms, you can do some of these factors better. And why is this result interesting? Like, why do we care about supermodularity or like approximate supermodularity? Is because of this theorem too. We say that for large classes, like as long as you have a p supermodular norm objective, there's a long list of problems which admit a good approximation. They admit a p approximation, order p, where think of p as being logarithmic. So you get a log approximation for these large list of problems. So what are these problems? Like many, many problems, like online problems, stochastic problems, bandit problems, online problems such as load balancing, online set cover, online packing, a bunch of stochastic problems such as adaptivity gaps for stochastic probing and decoupling inequalities. There are bandit problems. So all of these problems, like, and there are many more in the paper, we are able to obtain good algorithms for general norm objectives as long as your norm is p supermodular. And because of theorem 1, basically for any symmetric norm, for instance, we have good algorithms for now all of these problems because symmetric norms can be made supermodular. And again, to clarify, some of these applications are old, as in some of these applications like online load balancing, there was alternate algorithm known, which can also handle symmetric norms. But many of these applications are new, like online set cover and online packing. Previously, we could not handle them for symmetric norms, but now we can. So this gives both like a new way of proving and a unified way of analyzing things. Good. So here's like a rough outline of the remaining part of the talk. I told you like how norms are very interesting, and now we'll discuss how symmetric norms can be approximated by supermodular norms, and then we'll talk about some applications before I conclude. So recap, the first theorem is that any symmetric norm can be approximated within a log factor by a log supermodular norm. And think of log as like a good approximation factor. So this proof goes in 3 steps. Rather than directly approximating the symmetric norm by a supermodular norm, we first reduce symmetric norms in the step 1 to the top k norm. So top k, the recall, it's like the sum of the largest k coordinates. Second step is to reduce top k norms to something called as Orlich norms, which I'll define soon. And the third step is to get a good supermodular approximation for these Orlich norms. So that's how the proof goes in these 3 steps. Okay, so among these, step 1 is, I would say, somewhat standard. Step 2 is, I think, new, but maybe not very difficult. And step 3 is in some sense the heart of the proof. Good. So let's first quickly go over step 1. So it's just reducing the symmetric norms to top k norms. And roughly this is true because of classical connections such as like Shor convexity and fan dominance theorems. And more formally, the precise lemma that we need, which is shown in our previous work, like last year, and also similar lemmas have appeared earlier in the literature as well, is that any symmetric norm can be approximated within like a good factor, like log factor, by max of top k norms, max of weighted top k norms. Okay, so it basically says that any symmetric norm can be pretty much thought of as a top k norm or max of top k norms. Good, and then the proof of this fact like is not very difficult. It basically goes by some kind of discretization trick. Like you write the norm in its dual form as max of linears, and then you just discretize these weights as powers of 2 and argue that because of symmetry, these weights can be interpreted as some kind of top k norms. Okay, so step 1, as I'm saying, is not really new. This is what has appeared a lot in the past. Step 2 is the one where we show that how to reduce top k norms to Orlich norm. So let me first formally define what an Orlich norm is. So an Orlich norm is given by a convex function, which is often called as the Orlich function. It's a one-dimensional function. So think of it as an increasing function, which has convex function, which has g of 0 equals 0 and g of infinity going to infinity. And the norm is defined as its minimum alpha for any vector x, such that if you sum up this g function of xi over alpha, that is less than equal to 1. Okay, so this is defined. And in the simplest example here is LP norms. For LP norms, you should think of g function to be like g of t to be t to the power. So if the sum of these xi over alpha to the power p is less than equal to 1, then the minimum such alpha is going to be nothing but the LP norm. But in general, you can work with any other g function. So as I was saying, like, and these Orlich norms are pretty fundamental in functional analysis and probability theory For instance, they appear like a lot when you talk about some Gaussian, some exponential random variables. Again, you define appropriately, choose the G function and work with these RLH norms. But it also has found many TCS applications in regression and fields. Okay, so now the question, our lemma, what is this lemma? This reduction, it's saying that any Topke norm can be approximated within a factor 2 by an RLH norm. And the proof is actually not very difficult. You basically just work with this hinge function. So take the G function to be the following. It's like, it's 0 from 0 to 1 over k, and beyond 1 over k, it increases linearly with slope. And like by simple claims, which is not very difficult to show, you can show that this approximates within a factor 2 any Topke. So this basically reduces Topke norms to RLH norms. And why are RLH norms interesting? The reason RLH norms are interesting is because although norms are usually high-dimensional objects, you're working with some n-dimensional space, RLH norms are really given by just this one-dimensional function, like this function g, which is a variable, which is a function of just one variable. So it's much more amenable, like much more easier to work with. And hence, like this step 3 is about making, as we were saying, like making these RLH norms supermodular. So we say that any RLH norm can be approximated with a constant factor by a supermodular norm. And the reason we are able to do this is because RLH norms are much more easier to work with. And more formally, this is the lemma. We show that any RLH norm, as long as this RLH function, the corresponding function g, satisfies some bounded growth condition, then it is supermodular. So what is this bounded growth condition? It's formally given in terms of like t times g. The second derivative of g is bounded by p minus 1 times g. That's a derivative of g. But this, the way you should think of this is basically this inequality becomes tight when the function g is t to the power p. So it basically says that as long as your growth, as long as your g function is growing at most like a degree p polynomial, then you're fine. Then you will get like supermodularity. That's the rough intuition to keep in mind. And this is what this lemma says, that although you're talking about these norms in high dimension, all that you really need to get supermodularity is a control on this g function for the RLH norm. And if it is bounded growth, then you already get supermodularity. Good. And the proof is, in some sense, simple, but it requires some careful calculus calculation. Our current proof is like, say, a couple of pages calculations. I'm not familiar of any shorter proof. So it's no real new idea, but you need to do some careful calculations. And given this lemma, the second lemma says that, okay, actually any RLH norm, for any RLH norm, you can approximate its original function g, RLH function g, by another function, which has this bounded growth condition. So by only losing a small factor. So for p being logarithmic. So we can approximate any RLH norm by another RLH norm, which has this bounded growth condition without loss of generality. And roughly the reason, the way we achieve it is like you approximate the original RLH function by sum of bounded growth functions, like sum of other bounded growth functions. And notice that if you sum up bounded growth functions, the sum is also still bounded growth. And the way you do this is basically you some kind of discretization. You like look at your original g function, look at all its the points at which it gives different value 1 over n, 2 over n, 3 over n, and so on. Like at these discretization points, you write this as like some piecewise linear functions you can work with, and accordingly you can decompose the original function as sum of some hinge functions. And for each of these hinge functions gi tilde, you can approximate them with some kind of a bounded growth function. So it's not very difficult, but like once you have the idea, like I mean, this basically these two lemmas put together gives this theorem, which is in some sense the heart of the paper, technical bit. Okay, so main takeaway from this part is that any symmetric norm can be approximated within a good factor by a supermodular norm, and we perform this in 3 steps. Step 1 is pretty standard, reducing symmetry to Topke. The second is to Topke to RLH, which has the advantage that now you really have to, rather than working with high-dimensional object, you just have to work with a single-dimensional function g. And then in the third step, we make these RLH norms supermodular by like decomposing them as sum of hinge functions. And now let me quickly talk about some of our applications. The paper has many applications. I'll just briefly talk about a couple. So first application is the online load balancing, which I like a lot. It basically has T jobs, like jobs arrive one by one, and you have n machines. Whenever a job arrives, it tells you how much time or size it's going to take on each of the machines. Like you have n machines. VIT is how much time job I is going to take on the Tth machine. Your goal is to immediately assign this job to one of the machine. And in the end, you incur a load vector, which is an n-dimensional load vector, where the ith coordinate is nothing but the sum of the jobs, which were sizes, which were assigned to the ith machine. So each machine has some load that is the sum of the sizes, and you are interested in minimizing a norm of this n-dimensional load vector. So the classical problem that has been studied a lot is the L infinity norm, but which was already studied in the 90s. They showed a log approximation, and LP norms also, we know log approximations from the 90s, like 30 years ago. Special cases of these problems go back to even much older, like from the 60s in the original works of Graham. Good. So the main question in this, which is still open, is can we obtain a polylog or a good approximation competitive ratio for this problem for all monotone norms, like any monotone norm? So we still don't know the answer to this, which is a nice open question. But what we show is that for any P supermodular norm, you can get an order P competitive ratio just by running the greedy algorithm. So what's the greedy algorithm? At the Tth step, just send the current job to the machine, which gives you the lowest increase in the norm objective. So the claim is that this greedy algorithm is already P competitive for P supermodular norms. And as I was saying, because we can make any symmetric norm, like a logarithmic supermodular, log supermodular, this gives you like a polylog competitive ratio for symmetric norms, or any other supermodular norm. And the proof is also very simple. It's the reason I'm covering it. It's just like two inequalities. Basically, you look at the final load to the power P, write this as sum of the increases, like at the Tth steps. Since each time step you are performing greedy algorithm, like whatever load your algorithm incurred, like yt is the load, the Tth step your algorithm incurred in some ith coordinate, you could have replaced this with whatever the optimum, hindsight optimum does. Could have done like whichever incurred y step. Like that was a valid move. The reason you chose to perform yt is because your algorithm's increase was less. So you do this, the greedy step, and then you just do supermodularity. You basically add a negative vector on both the sides, which only can increase things because of supermodularity. And now you get a telescoping sum, which just simplifies, and you are just done with the approximation ratio. You get an order P approximation. So this is like a very clean application, clean and short proof, which not only reconstructs these previous results, like from the 90s and many others, but also it gives you like a very short proof for even other things, as long as your norm is supermodular. And which we know, like not many classes of norms are supermodular. Some other applications are like online coupling problems. So like you might have heard of problems like online set cover. So where you are interested in minimizing, like when you're thinking of this, you're interested in minimizing the norm X given some coverage constraints. So these coverage constraints are arising one by one. So you can only increase the coordinates. So you start off with all 0 vector. In each Tth round, the constraint ATX greater than or equal to 1 arrives. AT is like non-negative. So you can increase X to make this constraint feasible. And your goal is to minimize the norm of this vector X. Again, this captures the classical online set cover problems. What we are able to show is that basically because, so although people knew how to solve this for LP norm, earlier people did not know how to handle general symmetric norms. But because of P supermodularity, we are able to just combine it with existing works and argue that P supermodularity is all that you need for some of these existing works for their proofs to go through. And hence, this gives you like the first log approximation for symmetric norms for discovering problems. And similarly, like online packing, where you want to maximize some objective subject to some norm constraint. There again, like previously people, here in the Tth round, you get the Tth column vector, and you have to set immediately the scalar yt so as to maximize your objective. Again, we are able to combine just our P supermodularity with existing algorithm and argue that P supermodularity is all that they need to make their proofs go through. And because now we know many norms are P supermodular, you get like these new applications. And the paper has many, many more applications, which I won't be able to talk because of lack of time. So to conclude, in summary, so we first introduced what is P supermodularity, which is like just norm to the power P should have non-decreasing gradients. And then many, many norms are supermodular, like in particular symmetric norms. And the way we proved this was via Orlich norms. And then there are many, many applications which only require P supermodularity. Some future directions, one is like, okay, what are some other applications of supermodularity and what other norms are supermodular? And another very interesting open question is more about like going beyond supermodular norms. Even like for arbitrary monotone norms, can we still design good algorithms? So we were able to show that, okay, not every norm is supermodular. There are monotone norms which cannot be approximated by supermodular norms. But what is the correct notion which can show that to get good algorithms for arbitrary monotone norms? Thank you.